Dana Howard, and I am a member of the Center for Bioethics and the Philosophy Department at The Ohio State University. Welcome to our monthly CARE panel, Conversations about Research Ethics, that is sponsored by the Center for Ethics and Human Values. The CARE program aims to support Ohio State's shared values in the domain of research by building community around discussions of research integrity. And it's presented with the support of the OSU Medical Center Center for Bioethics and the Clinical and Translational Science Institute. We're so happy to have all of you, and I am so delighted to have this great panel. So the session today will explore the ethical and practical aspects of reproducibility in science research. With renewed national focus, such as recent executive orders and the proposals that come from HHS and the NIH, emphasizing the importance of replication studies, questions about whether science faces a replication crisis have become at least more politically salient and pressing. So what defines a reproducibility problem? What are the ethical responsibilities of researchers, of funders, of institutions, and of the federal government in addressing it? And I am so delighted to have the three of you panelists today. For our external expert, we have Dr. Berna Devezer, who is the professor of marketing at the College of Business and Economics at University of Idaho and is affiliate faculty at the Department of Mathematics and Statistics and Statistical Science. Dr. Devezer's scholarship focuses on advancing models and theories of science, also called metascience. And her research is deeply interdisciplinary, bringing together statistical theory, experimental methods, mathematical modeling, philosophy and history of science to advance understanding of the scientific process. And she asks questions about the objectives and values of science and the role of replications and reproducibility of scientific findings in advance. So welcome. First, we're going to have Berna present for around 20 minutes to just give us an overview of her own scholarship and her own framing of whether or not there's a crisis and what are the ethical concerns that come with that. Then we will have Elizabeth Campolongo, who is a senior data scientist at the Imageomics Institute and the ABC Global Center at OSU. Elizabeth works on data-driven biological trait discovery and understanding through the use of machine learning and computer vision. Much of her work is centered on exploring the vast potential of biodiversity data, all while ensuring research is both fair and reproducible. And then we will also have Dr. Phillip Popovich, who's professor and chair of the Department of Neuroscience, executive director of the Belford Center for Spinal Cord Injury, director of the Center for Brain and Spinal Cord Repair, and faculty affiliate at the Chronic Brain Injury at Ohio State University. Wearing multiple hats, Dr. Popovich does a lot of things at OSU, but Phil's lab is engaged in two main research questions. One is what causes myeloid cells to both help and harm the injured spinal cord, and two, why does spinal cord injury cause pathology in organs found throughout the body? I am so excited to have the three of you here to sort of have this discussion. We'll start with sort of introductory remarks, followed by a set of questions that I came up with to just get the conversation going. And then for participants, you will have a chance in the Q&A to ask questions. Please just start asking questions whenever, and we'll get to questions for the last 20 minutes of the session. So to no further ado, Berna, why don't you get us started?
Hey, thank you so much for inviting me. This is kind of a topic near and dear to my heart. I'll just try to give some brief remarks as you asked for, but a lot of this is going to be based on our research spanning over almost a decade now. And I'm not going to be able to go into too much detail. Hopefully in the Q&A, we're going to be able to follow some of these threads a little bit more in depth. So I titled my talk, Reproducibility Crisis is Not Real, but it can hurt us. So I can stop here. It kind of gives the whole idea. But, well, I'm going to try to build up to that, why I have this opinion. This is kind of a selection of my colleagues and I have been working on meta science, especially from a theoretical perspective, in the last, well, close to a decade. And we've worked a lot on reproducibility, replications, trying to understand the nature of experiments, scientific exploration, discovery. This is some of the select articles that I'm going to kind of tap today, not directly, but I'm going to draw from them. But there is more that we have published and we're working on. If anyone's interested, just let me know as a follow-up later on. So let's see. My core position today, given the topic of the panel, is that reproducibility crisis or replication crisis, whichever label you use, is simply rhetoric. It's not a fact or established fact. I also find this crisis narrative reductive and very prescriptive to kind of lead research and drive resources, and not really descriptive of what science is and how it progresses, and not at all explanatory about what are the things that we're dealing with, what are the problems, and what are the root causes of those. And as a frame that is used to drive scientific activity and to inform science policy, as we see nowadays, it really is not cost-free or harmless. So that's the core position. I will build up to it by kind of breaking down this phrasing or framing of reproducibility crisis or replication crisis in science into its components, into its assumptions, and try to lay out that a lot of these assumptions are not verified or not verifiable. So let me just start breaking it down a little bit. First, I'm going to focus on the crisis bit in that. So just the claim that there's a crisis in science, it makes a lot of assumptions, a lot of unspoken assumptions. So let's start with the definition of what a crisis is. So it's a time of intense difficulty, trouble, or danger. Some of the synonyms are catastrophe, calamity, emergency, a disaster. It's supposed to be a time when a difficult or important decision must be made because this is a turning point or a crossroads. So this turning point may lead to two potential outcomes, either to recovery or death based on the kind of decision that you make. So basically the designation of crisis to these reproducibility or replication issues assumes that science is currently going through a particularly catastrophic period akin to a disaster or emergency. And the observed reproducibility issues demarcate this turning point, and science currently is at a crossroads, has to make certain decisions to change this course. And if science does not make the right decision, the risk is an imminent death for science or a collapse. So this is kind of it's a very particular kind of narrative, which I find is not really supported by evidence. We don't necessarily have an evidence of a catastrophe or disaster. It's either scant, in here or there, we have like a few demonstrations and evidence for lack of reproducibility in certain subfields and certain samples of studies. It's also weak and fragile, as I find. It's not necessarily robust. It changes with how you measure reproducibility. It changes with how you sample studies. So it's not very reliable at that. There's also no sign of a major turning point or new era in science, in the sense that I recommend everyone to kind of read a little bit into history of science, but one of my favorites has been Ha-Seok Chang's work, especially these two books, Inventing Temperature and Is Water H2O, where he shows, like, in different periods in science, in chemistry, in physics, lays out in detail how research has progressed over a few centuries. And we see that lack of reproducibility has always been an issue. There has always been a lot of experiments that scientists have failed to replicate, which normally should fuel more science. Like it actually starts, ignites more questions, leads to more research, more exploration. And the way we observe science is not really looking at each of these individual cases, but over a long period of time, how it evolves and how we learn from these things. So it does not necessarily seem to be that we're in a particularly special era of time where these issues just came about. Like suddenly we are not able to reproduce things. There's also, we don't have a benchmark to expect any level of reproducibility rate at any field at any given point in time or a stage of progress in science. Should science be 90% reproducible? Should it be 60%? Is 20% too uncommon? Is it too like way off? When is that acceptable? What should that yield, or what kind of process should follow from that? We don't necessarily have a good benchmark for any of that. We don't know what it should be, but we feel alarmed when we see that it's 50%, let's say. And why? Like there's no real explanation for that feeling. And there is no evidence that science faces collapse without immediate action. I mean, this is really a very serious statement, and it's very difficult to make this conclusion based on what we see right now. So in my view, this crisis framing is catastrophizing, and it's primarily rhetorical. And the purpose of it is to drive resources, to lead funding, to draw attention to certain issues, but it kind of takes over. Like it's taken a life on its own, so it's become a whole crisis thing now. The second part of this framing is the focus on reproducibility and or replications. So making the crisis about reproducibility, so it's either a reproducibility crisis or a replication crisis, also makes certain assumptions. First, this interchangeable use assumes that replication and reproducibility issues are equivalent. So basically it says that like the fact that we cannot reproduce the results of a finding versus we cannot replicate a study because there's no open data or like the code is a mess are the same thing, but they're not really. They're not necessarily equivalent. Replication as well, it also assumes that replication is a concept that we well understand and we can easily design high quality replications. Hence, it assumes that replication studies should be prioritized and should be epistemically privileged in the sense that we don't necessarily need a justification, any external justification to run a replication. Science should be doing this all the time, so we should be replicating everything. It assumes also the reproducibility crisis framing assumes that we understand reproducibility as a concept and we can measure it, especially via replications. And the most important maybe assumption is that low reproducibility signals something bad. Like it is a signal of some kind of, failure or disaster. It's either epistemic failure or an ethical failure. And if we can increase reproducibility rates, that will restore science to its, I don't know, maybe glory days or something. So what is the evidence with this regard? And here on this part, I'm going to draw a lot from our research, what we have found in the last decade. So first thing, the ability to replicate and ability to reproduce results are completely distinct concepts. They have different drivers, they have different outcomes. They're not necessarily always related. The fact that we can replicate something does not guarantee that we're going to be able to reproduce the results. The fact that we can reproduce some results does not mean that the experiment was perfectly replicable. So they need to be evaluated independently. Also under this one label, diverse problems from publication bias, which is a systemic problem, to statistical illiteracy, which is an educational training level problem, to fraud, which is a very particular type of problem and maybe much narrower, to weak theory, poor measurement, bad sampling practices, maybe lack of transparency, not sharing data. A lot of things are grouped together under one label, and we refer to replication crisis. These are different problems. Like these are not the same thing, and they do not necessarily have the same outcome either. They don't always lead to lack of reproducibility, for example. We cannot diagnose these problems based on that. Another assumption here is that exact replications are impossible. Another evidence against the assumption that we can run well-informed, high-quality replication is that exact replications are impossible by nature of the thing. And we end up running a lot of non-exact replications, but we find that we make wrong inferences from these non-exact replications. We do not know what kind of evidence they carry. They are not diagnostic with respect to the effects that we're interested in. And we ignore like what a non-exact replication, what kind of noise or bias it may add to the process that's being ignored. We find that replications of most experiments also lack diagnostic and evidential value. And that's different in the sense that, I mean, most of the experiments we run are not replication ready. They should not be replicated because they are not, the designs are very noisy. The measurements are not there. The sampling could be improved. Maybe we need to advance theory a little bit. Maybe we need to be finding a better way to manipulate things. So replicating experiments that we know to be faulty or poorly designed or not diagnostic is really not a good idea. Like it means like we're rerunning a bad study. So that is a problem. And measuring reproducibility, we're really not good at that. A lot of these metrics that we use to measure reproducibility, they're inconsistent. They bring a lot of noise. They do not give reliable information based on a single replication or even 10 replications. So a lot of our work actually finds that you would need like thousands of replications for your estimates to mean something. And they are incomparable because a lot of studies use different kinds of metrics to measure reproducibility, and they do not compare. And we try to compare and make sense. And there was this recent case that I was kind of part of, you may have heard of it, a very high-profile study that found high levels of reproducibility was retracted at Nature Human Behavior based on like some commentary that we wrote, my colleague Joe Coleman and I. Sorry. And they used a reproducibility metric to claim that some of these recommended rigorous research practices like pre-registration leads to high reproducibility rates. They used a metric that has not been used before in the literature. It was so unique that it didn't compare to anything. And when they used a metric that was similar to what was used in the literature, their reproducibility rates dropped to like 70%. So really, we're not able to measure this with any kind of accuracy. Reproducibility rates also do not track scientific progress or reliability of science. So we have studied this extensively. So I kind of cite 3 of our papers here, but really a lot of different scientific processes, different kinds of mechanisms may lead to the same identical low reproducibility rate or high reproducibility rate. We can find true results that we cannot reproduce. We can find wrong results that we may be able to reproduce with 100% accuracy. So it really does not track what we think it does. So my conclusion in this section is that replication and reproducibility are largely misunderstood. They're misdiagnosed too as problems. And as a result, they are being misused currently in this science reform framing. And finally, the last bit in this phrasing, in science, which makes a whole lot of assumptions, really. Basically making the whole crisis into a science-wide problems assumes that first, the issues that were initially observed in social psychology are transferable across other disciplines. And then it also assumes that when we find evidence in different fields about similar issues, they are the same. So the same process leads to them. And they can be, hence, we can generalize that to all of science. And it assumes that the observed replication or reproducibility issues suggests scientific progress has in general stalled. So that makes it into a crisis at the level of science. Hence, as a result, all disciplines need to prioritize replication studies and increase reproducibility rates. That's the proposed solution. So I think the evidence here is like we don't need to look far for it. And I don't even need arguments for that. Just look at science. Look at what has been happening elsewhere in science in the same time frame that the reproducibility crisis has been happening, right? Like we have the Higgs boson, we have the mRNA vaccines that have been developed during COVID-19 pandemic in a very short period of time, the cure for sickle cell disease, the gravitational waves. You can't keep adding to this list. It's obvious that science has not stopped. Like it's making progress somewhere. So, but I mean, to turn it into some kind of formal argument, social psychology is very unique. Like it has its own subject matter, its own methods, its norms and constraints. And it's not really generalizable to all of science. It's a very particular frame or a very particular domain. Meaningful analogies can be made across sciences, of course, and philosophers have been doing that, but it requires a lot of careful study, historical study, sociological understanding of the dynamics within these fields, philosophical study, and none of the replication crisis narrative has been based on this kind of comparative approach. No systematic attempt to date has mapped reproducible traits to actual scientific progress. So that the correlation that we make there is basically an assumption. There's a huge gap there, research gap, and no one has done this. Low reproducibility in multiple fields may arise from entirely different mechanisms, as I said, and some of it might be healthy, some of it may not be. And no evidence indicates that overall scientific progress has stalled in a way that we need to generalize this crisis to science. And the role of replication studies in driving progress remains unclear. So like if science has stopped right now, how is replication going to help with that? So that part, again, like a lot of assumptions happening there. So my take from here is that science is not a monolith, and we should not be treating it as such. We should not be losing complexity and meaning as we analyze problems in science, because we know that scientific progress continues. So to wrap it all up and bring it to these ethical issues that we want to discuss, the crisis framing is not only wrong, factually wrong, but it causes epistemic, ethical, and practical harms. So this replacing actual scientific inquiry with rhetoric itself it's dangerous, I think. We're losing what science is all about. We're losing what we're capable of or what we're supposed to be doing. And we're lending all of that or swapping all of that with some kind of rhetoric that we think is going to help us in some fashion, but that's not how scientists do things. We should be more curious about what are the facts here. This framing ignores scientific complexity, diversity among sciences, heterogeneity, and it creates this, homogeneous, unified narrative. It diverts attention and funding from actually understanding science and addressing real problems in specific fields, narrow problems, well-defined problems, well-understood problems. So instead of trying to, for instance, understand what are these specific issues in different fields, we're trying to create this into a huge, humongous, kind of amorphous mass of an issue that we cannot even define and pour resources into that. So it also ends up wasting resources on low-value replications, which in our research, we analyze quite a few replications and we find them lacking terrible designs. They're not capable of doing what they claim to be doing. Those studies should not be run. They're extremely costly, mass studies, large samples, multi-site studies. We pour a lot of resources currently on that. And there's a lot of especially private funding going into supporting these replications. They're really not good. Like the data is extremely noisy. You cannot make clear inferences from them. And one thing that this framing or the focus on replication does is it overemphasizes single studies as progress indicators and kind of reifies this myth that every scientific study is supposed to contribute a scientific fact. Whereas we know that that is not how science progresses. Like, we do not necessarily learn facts from individual studies. We learn from programmatic research. We learn over time. We have to do a lot of exploration to actually arrive at anything that resembles a fact. So this focus on replication as an arbiter of truth is extremely misplaced. It's also a way to evade uncertainty instead of dealing with, what we cannot know. We try to kind of take a shortcut into making premature conclusions. Okay, like this does not replicate, let's stop working on it. That's bad. That is just poor science. And it promises simplistic, untested solutions to ill-defined, complex, potentially multi-causal problems. And thereby it does end up reducing public trust by masking real scientific progress. The real scientific progress takes the back seat, and we highlight, see, like, science does not work. We have so much fraud. We have so many things that don't replicate, instead of trying to understand that science has always been a mess. Like, when you look at any period in science, there's so much mess, but the scientific process is really working through that mess. And that's what we're doing right now, and kind of hiding where the progress lies in favor of such a narrative really does reduce public trust in science. And finally, I think this leads to an exploitation of science for political agendas, as we see in the gold standard science, the executive order. It appropriates a lot of the scientific reform, replication crisis literature, and the language, which really were kind of making it possible by creating this narrative in the first place, instead of, targeting problems where they are, being specific about it. We make this monstrous thing, and then the monster is here now. Like, it is causing harm. So with that, I'll stop here. Thank you very much for listening to me, and hoping to address some of these a little bit more in the Q&A.
Thanks so much, Berna, for that informative and forceful opening sort of introduction. So maybe we'll go to Phil, and you can sort of share your own thoughts, how you've been thinking about reproducibility in your own lab, and also maybe as sort of a mentor for others.
Yeah, thank you, Dana. Yeah, I'll be very brief. I don't have slides. I think that me sharing my experiences briefly will provide some context for maybe some additional questions. I thought Berna's presentation was fantastic. She really hit on so many really important key points that I think we really should focus on in the discussion. But very briefly, so I'm professor and chair of the Department of Neuroscience, and I've been running an NIH and DoD funded research laboratory for about 30 years. So through that time, I've trained dozens of students, postdocs, and even junior faculty. When I really became acutely in tuned with the issues of reproducibility and replication was right around 2007, when the NINDS, and specifically our program officer within NINDS that managed the spinal cord injury portfolio, she decided that because there were so many high-profile papers coming out in the spinal cord injury and neuroregeneration field that were unable to be replicated, that she wanted to explore some of the causes for this. And this was kind of a pivotal time, because this actually preceded by many years the Office of Research Quality that now lies within NINDS. And what we learned during that period was a result of a competitive contract program that Naomi Kleitman, who is the program officer that I'm referring to, she wrote a contract where multiple laboratories from around the country wrote applications to compete for dollars that were specifically earmarked for replication, much like is being proposed right now on a general basis at the NIH. But this is specifically within the area of spinal cord injury. So people had to have real demonstrated expertise in modeling and various outcomes assessment tools that stood the test of time in order to actually be prepared and qualified to run replication trials. So we competed at OSU and we won one of these contracts. There was another contract that was won at another institution in the US. And the idea was that we would simultaneously work on identifying and replicating promising observations that had been published in the literature. There were no limitations on what the study was or what the outcomes were or where they were published, but we had to have a committee that helped us vet the ideas and describe, a reasonable way why we thought it was important to replicate. To make a long story short, the contract lasted 5 years. The contract specified that we had to try to replicate at least one study per year. And over the period of 5 years at OSU, we replicated essentially 1.5 of our 5 studies that we tried to replicate. Now, I say half because it's complicated in what actually constituted a replication, much like Berna described in her slides. There's many facets to replication, and some of what we tried to do, we were successful doing, some we were not. The outcomes from these contracts were, they led to some high-profile papers on issues that Berna described. They were published in Nature. They were discussed amongst NIH leadership, and they served as authors on these papers. That ultimately did lead to the Office of Research Quality. And so this was a predecessor to that. And it's now very much baked into the culture, at least in the spinal cord injury research community, but also has spread into the stroke research community and other areas of neurological disease, as well as cancer research, et cetera. So this is a big issue now. And all I can tell you from my experience, and I'm happy to discuss and answer any questions that are specific to why is replication so difficult. And I can give you very specific examples from my own bench experience doing this, but it's very, very difficult to replicate a study, even when you talk one-on-one with the original author and original research team of a project, which we did. We spent many, many hours on phone conversations, Zoom calls, et cetera, going back and forth, details through the methodology, even some of the methodology that wasn't present in the published papers, to try to make sure that we were replicating studies with high fidelity to the original claim, right? And even when we did that, oftentimes receiving materials from the other laboratory, it's very difficult to replicate a study. So with that as a background, I mean, I have my own personal opinions on everything that Berna said, and I don't disagree with anything she said, but I think this is a pretty hot button issue for anybody who's in science right now, and it should stimulate, the rhetoric should stimulate concern, but hopefully it does stimulate the conversation that Dana wants us to have today. With that, I'll pass it off to Elizabeth.
Thank you. I will say I find what both of you said very enlightening and things I've seen. I think I'm coming from a rather different perspective, as I did my PhD in pure math, where you present your theorems and you should be able to read through a proof and follow the proof, and the proof should be, that's kind of, you build in mathematics. And I transitioned into data science and have done some quantum computing research as well. And there's, when we get into those areas, it's a lot more looking at what is the evaluation metrics, I think, is a lot of what we spend our time focusing on, and how we evaluate. Specifically with the Imageomics Institute, we're working in this very young field of imageomics. As we see that omics of images, we're trying to understand what we can learn, specifically looking at a lot of biodiversity and ecological applications. What can we learn from images? Because everyone's out there, you have people taking pictures on their phones. You've got a lot of museums working on digitizing their collections to make this work and these intense data collection regimes that have happened over centuries more accessible to more researchers in different places. But then we get at this challenge of, okay, you've trained this machine learning or AI model, and now it's giving you some result. Now, what is it saying? What are these predictions that it's saying? And can we trust it? Can we believe it? If I give it, the same input multiple times, is it going to give me the same answer? And these kinds of big questions of how do we understand what is coming out of these models is more where a lot of the focus relies on, because as Berna was saying, can we build science? We can build science without being able to, I can't go retrain these large language models, but we do try to focus on building on open source models. So you at least know how it's being done, presumably, and what is going into it, to be able to make a scientific inference at the end. So a lot of our work has been focusing on trying to better understand how we get from the input that we're given, and then, well, can we actually make inferences of this? Is this scientifically valid? Can I do the same biological analysis that would be done with this data? And can I reproduce a lot of it now is this question of, are we reproducing results that already have been done with these models? So are they a reliable partner? And I think this is a big question as there's the push for these, your AI scientists and all this question. And so my perspective here would be, I agree with everything that you've said. I think that it is a buzz, and it does depend on your field, and it depends on your frame of reference. So a lot of what we're trying to do is understand, how do we tell if the answers we're getting are realistic? Can we define a bunch of different benchmarks on which we can train models to see what they actually understand, or if they're actually a valid tool to be used for this particular research? Is it answering the question that you're looking for? And that proves very difficult. We have some benefits with resources like GitHub and such, where I can put my code out there, people can ask questions. There's a lot more give and take. So I think certain elements of these pipelines are more reproducible than others. They're more replicable than others. But you also have challenges when you're using open source or publicly available data. A big challenge is like link rot. Your URLs might disappear, but I'm not going to republish a bunch of images that somebody else has published, because that's then infringing on their rights. So we focus a lot on this. How can we process it, and making sure that at least the end product is out there and the end product can be evaluated, and that evaluation can be redone by somebody still getting the same results. So I think those are areas that people have been working very hard, and more broadly in the computer science community, there's a lot more push for the openness of your data and your code. And I think that helps in being able to, if not reproduce, replicate the model by retraining. You have the model weights and you have the evaluation, and you can see, yes, it does do what it says it does.
Well,
thank you.
Yeah, thank you so much, Elizabeth, Phil, and Berna. I feel like even if there's like sort of a general consensus, it's like really useful. I feel like the conversation so far has been a little bit of like a breath, where we're like, okay, let's actually like think about what we care about when we care about reproducibility, because it seems like people care about something, right? And I'm going to just ask some questions that I came up with. The participants have already started asking Q&A questions, so please continue asking those questions, and we're going to get to those shortly. But just to get the ball rolling, I mean, one thing that struck me, Berna, and I think it was a thread throughout what each of you have said, is this idea that reproducibility is not a good marker for reliability, right? And it's like, I mean, we want to get reliability, right? And so one of the things, I mean, this is sort of a general question, but are all failures of replication bad? And are they symptoms of unreliable science? Should failure of replication undermine our trust in the results of the original study or the program? Should we be like, what should we be aiming at, right? If it's not sort of this direct replication of studies, which seems to be so incredibly hard. So Berna, why don't you start, and then Phil or Elizabeth, you could jump in.
So the difficulty there is, I think, the reproducible. I mean, there are many kinds of irreproducibility. Many things may lead to us not being able to reproduce a finding. Some of it could be just because of the nature of the thing. Some things we cannot repeat. It only happens once in a time. So we're going to have to kind of work with that. It's no reason to not study it scientifically just because we cannot replicate it. But we know that it's not going to be reproducible. Some things, the nature, we find in our research basically 3 categories of things that lead to variable results in reproducibility. One, the most important part is we tend to assume that reproducibility tracks some kind of truth about the nature. So if there's a phenomenon, and if one research showed that phenomenon, that should be reproduced in other research, or it should be replicable. So that assumption really does not hold. It really comes down to very simple simulations, and you can find that a lot of times that's not what reproducibility tracks at all. Truth is only a very small part of it. It tracks starting from sampling error, any kind of error you can find, like model misspecification, it tracks that. It tracks measurement error that we may not have accounted for. It tracks bad sampling practices, which is kind of, again, this whole thing started in social psychology. There is no sampling procedures there. It's like the student convenience samples or MTurk, basically. So like very poor sampling quality. It can track different maybe errors that we make in our statistical analyses. So it tracks really a lot of information about a specific study rather than any kind of underlying truth that we may be able to observe or we may be interested in observing. That's one thing. So our studies are far from being perfect. And a lot of the focus, I think, in the reproducibility crisis and science reform community has been on the assumption that we need to replicate things because of sampling error, because, we may have kind of hit on something just randomly, so it's going to help us eliminate sampling error. But really, let me tell you, sampling error is the least of our worries. We know how to take care of that. There's a lot of different kinds of errors in any kind of study, and those are the parts that inflate the noise in the systems that we're trying to study. That's why replication is not gonna really settle that. It's impossible to do that. The second thing is replications themselves are removed from the actual study. As Phillip said, it's very, very difficult to have a high fidelity replication study. A lot of times in many replications, that's not even attempted, the high fidelity. It's just, there's a lot of assumptions. Okay, we could not use this maybe measure, but we're going to use a substitute for it, or we have a different sample, or we cannot use the sampling scheme, or we're going to have, we have missing data, we're going to treat it in a different way. You introduce so much variation in the replication. So now replication is its own study. It's not really trying to do the same thing that the first one does. It does something completely different. And to the extent that it carries any kind of evidence or speaks to the validity or reliability of the results in the first study, we do not even study that. So it requires a lot of formal modeling to be able to deal with that kind of variation. And the third thing, of course, is how we measure reproducibility. Whether you look at statistical significance, whether you look at overlapping confidence intervals, whether you look at prediction intervals, whether you come up with your own reproducibility metric, all of these are going to give you different results. So again, within the same study, you can calculate reproducibility rates that are 98% and are 70%. That's the same data, same everything, just metric difference. Considering everything else, the failed replication could be a symptom, but of what, we don't know. So that's what should fuel the further research. So we need to figure out now, why did this happen, instead of saying that replication holds, that's the final result that we get. This area just is whole, let's throw it into trash. that's not the right approach. Really, it is symptomatic of so many different things. We just need to pinpoint it. We need to do much more research to figure out why. So yeah, that's kind of my take on it.
Phil, you promised in your opening remarks that maybe you could go through like an example, but I'm interested, you know, in your field, what does cause you concern when it comes to like a lack of replication, and what do you think is just sort of part of the doing of science?
Yeah, I mean, maybe I can reframe this a little bit in the context of the question, one of the questions you posed to us, and that is should a failure of replication undermine our trust in the results? And whether it should or shouldn't, I think the reality is that it does, right? I think most people, most scientists, when they hear or they read a paper that attempted to replicate and the results are negative or even opposite of what the original publication showed, it raises questions about that individual's work or the robustness of the biology that underlied that finding. What we really should be doing is asking why it was that way in the first place. And we don't really have the way the current structures for disseminating and reporting science exist. We don't really have platforms for this. Normal scientific publication does not allow for us to talk about data shortcomings and limitations in experimental design. It doesn't provide the space for complete transparency and build up to the actual experiments that were done to produce the data that goes into telling the story about whatever the final outcome is. Let's face it, science papers are stories, and the story rarely occurs in the order in which it's presented. And each one of those data sets that you see in a polished figure probably took years to generate, and I guarantee you many failed experiments that aren't discussed, but that laid the foundation for how that ultimate experiment was designed. And we don't talk about much of that, even in a professional scientific meeting when we're there and we're with our colleagues, because who wants to talk about that? They want to talk about the results, right? But the reality is that I found out during the replication contract that a lot of that was very important for trying to actually develop a valid experiment and to challenge why I wouldn't have done it a different way, right? Because oftentimes people will try to do it a certain way. Let's say I'm trying to replicate a study and I've always done things one way and I know that it does essentially the same thing as something that's done in another person's laboratory. But my lab's very good at doing it this way and I'm just going to do it this way. Well, if I do it that way and there's a subtle difference in the approach, but the biological implication's huge, but we don't know it, that can produce a result that's completely the opposite. And we found that out during the replication studies. It took us about 1.5 years to figure it out through a lot of discussions that there was one subtle change. We both injured spinal cords, but we injured them in a way that had an impact on biomechanics and it had an impact on the anatomy that nobody knew about. Nobody did. So we made a really important discovery, but it resulted in a failed replication. Had we not had the conversation with the author, we never would have figured it out. And we would have had a paper out there that said that this project, this therapy that was tested did not work in our hands and people would not have trusted it. So there's really so many details about this that the lay public won't understand. And we don't have a forum really to discuss it with them to make them understand the scientific process and what goes into actually performing an experiment. But all that information is critical. And I can tell you that laying aside money to actually do replication studies, having been the beneficiary of a significant amount of money from the NIH to do this, is not the answer. It may be in some context. There may be certain situations in which, yes, putting some money towards trying to replicate something, but if it's got to be so clearly defined. But I can tell you that most of that money will be wasted or will yield data that is negative and doesn't replicate the original study. So all we're going to be doing is fueling this so-called crisis when in fact there really is no crisis. I really think that if they want to put money into a problem, they need to put money into changing incentive structures, changing institutional practices and expectations for how scientists move through, promotion and tenure, et cetera. There's a lot of different areas where the government and the NIH can influence this process in a beneficial way, but I don't think that's the goal.
So I'm going to jump into the queue and just sort of ask a follow-up question from one of the participants, because I think this is really related to what you just said, Phil. So Diego Alzate said, maybe this can be a turn on the semantic issue about whether or not this is an incorrect label, whether or not this is really a reproducibility replication crisis. But there are issues such as p-hacking, data falsification, publication bias, et cetera, that still need to be addressed, without mentioning the incentives that may lead to many scientists to fall into the wrong practices. And I'm wondering, we're a little bit going out of order, but I'm wondering if you have any sort of suggestions about thinking about, like, what would it look like for us as a scientific community to have successfully addressed the sort of concerns that are at the sort of heart of what people worry about when it comes to the replication crisis.
I mean, I'll take a stab at it, but I do not necessarily have a clear answer to that. It's like, I think what's being imagined that would come out of it is an idealized version of science that doesn't exist, that has never existed. Like, the assumption is that we're never going to make any mistakes. That every single study that we run from the get-go is going to find something. So like that just doesn't exist. It's kind of trying to, it is scientism. That's the outcome that they want. Like, it's the scientistic view of science, not the scientist's view of science. And it's not a good vision. It's not realistic. So I really don't know, like, what it would look like if we fixed all of this, because I can imagine a world where we carve ourselves some artificial research questions that every time we test in the lab are going to be 100% replicable. That can be done. We can find, like, we can train our measures, we can train our methods to do this, create perfectly reproducible results. It's not that difficult. The easiest form is, like, if you fix your alpha error to 1 instead of, like 0.05, everything's going to be 100% reproducible and 100% wrong. Like, so we don't want to do that, right? So, I mean, we don't want to artificially fix this problem that we have created. We want to be able to fix real problems. So p-hacking, for instance, could be a real problem, but because of this framing of crisis, we cannot even evaluate that realistically. There's some research that suggests that the p-hacking does not necessarily lead to, like, it's not single-handedly capable of resulting in a lot of fake findings. Like, p-hacking is done typically in a certain way. It's only maybe, adding a little bit bias, but if it's added up, it doesn't really affect, like, general error rates that much. So there's a lot of we should be asking these questions a little bit more. It's wrong, but the fix for that is not really to push replications. The fix for that is, how do we fix our statistical literacy issue? Like, how do we make people actually understand and care about statistics and not necessarily care about the p-value that they get? I mean, those are completely different questions, I think, like different ways of framing the problem. Hence, the solutions that are being proposed is like pre-registration is not going to do anything about p-hacking. If people want to p-hack, they're going to p-hack, pre-registered or not. And they are. They are p-hacking studies that claim pre-registration is good, and they claim pre-registered, everything is pre-registered. So, I mean, that's not, the cures do not match the problems, and they really actually end up undermining the real problems that we have. So yeah, how would that science look like? It wouldn't look like science, is my feeling.
So maybe I'm going to direct this question to Elizabeth, because I mean, I think that there is a sort of interesting question related to machine learning and sort of using AI models in general for like some of these issues. And one of the questions that has been framing this discussion is like, is there really a crisis, right? And one of the things that I'm interested in to hear from you is like, should we be worried about the failure to replicate studies in certain fields versus others? And I'm wondering what you think about the sort of use of AI and machine learning, and like how, like, is this more worrisome, the fact that like these models are not replicable than in using other methods and tools for research? Or yeah, just to hear your thoughts on that, and maybe sort of to piggyback on the discussion that we were just having, like what are some things we can do to try and sort of respond to the concerns that people are having related to the reliability of the research?
So I think my biggest concerns in AI or ML use is people using it that don't understand it or like misuse. I think that's the biggest danger to science is people relying on, especially the closed LLMs, like the large language models. Sorry, I'll try to avoid too much jargon. Like ChatGPT, Google Gemini, using these models they are trained on massive amounts of data, basically the internet. What actually goes into their training is beyond the scope of what people can easily assess and analyze, and they're closed. There's no open source. It's not something there's no GitHub repository that I can go to and I can find the model weights and I can find the training regime and I can understand exactly I can understand at least the method by which these things were built, and I can't go look up their data and see what's there and understand what was put into it. And these are they're black boxes. You put something in and an answer comes out. How it's coming up with that answer and whether it's doing that based on what I actually put into it or based on all of the information that it has seen and it's just making an assumption because of what I put into it, that would be personally, that's my biggest concern is these. And these are things we've tried to look at and using them like for making assumption or learning about trait similarities between different species. So we had one project that tried to understand, okay, are these vision language models actually seeing the image? Do they have an understanding? If I ask it, where's the pectoral fin on this fish? And getting at, does it see that there is a pectoral fin? Does it know what that is? Can it locate it in the image? Does it actually understand? And most of them, there are some that it's like, okay, well, this is common knowledge. It can kind of figure out the tail fin, but what's a pectoral fin is more complicated. And when you start digging at these things, they don't understand necessarily what people think they do. Um, so I think that gets at a lot of it. And what one motivator, which I think I would like to think is helpful. So a lot of these things get published on the Hugging Face platform, which is very similar to GitHub in that it's version controlled, but it's for large files, and this is where models and data used for computer science are often published. And they've introduced a while back now data set and model cards, which have these categories for things for people to describe more of what it is, basically the process that they went through to create these, link out to their GitHub repositories where they've developed it. And they have these sections for like out of scope use. So what is the intended use? What is the out of scope use? What are, biases, risks, and limitations of using these things? Basically trying to get people to think about, well, what shouldn't this be used for? What are some of the challenges here? Why should I not use it? Getting at a bit of the what is it safe to use this for? What is it not? And I think understanding that using a model that is not designed to do the task that you're using it for, it's like, okay, well, I'm not going to use a hammer to put a screw in my wall, right? So why would I use a model that's trained on, cat photos on the internet to try to understand fish morphology. It's the same kind of idea. And I think that's where getting at that transparency that I think both Phil and Berna have gotten at as being part of how studies are replicable or at least reproducible in their findings, that transparency is so important in the understanding.
Yeah, so thank you so much. And we could now transition a little bit more to the ethical dimensions of this, which I find fascinating and really hard. We've touched upon, so I want to get to the question about public trust in a second. But one thing that, Berna, you touched upon is sort of the costliness. Like, it's not cost-free to engage in replication studies. And Phil, you also mentioned this sort of concern about wasted resources. One thing we haven't talked about that I'm interested to hear your thoughts about is the sort of extra risks and burdens that we may be putting on human participants and actually animal subjects when it comes to these replication studies. Like, are there ethical concerns here about actually engaging in replication studies, given everything we've already said about the potential lack of epistemic value that they have in moving forward science and scientific progress?
So I think it's not different from any other research project, right? So that's how it should be evaluated. Like, we should always, it's ethical to maybe perform the best study you can at any given point. Like, if you know that there's a better study that you are able to run, that's what you should do. So that's what we're missing, I think, with replications, especially because there is now specific funding and attentions focused on running replications, where the assumption is that we do not need to justify these. Like, replications are good, are kind of almost like a natural good. Like, we don't have to worry about that. And that's not the case. I think that at the minimum, what we should do is evaluate every single replication study just we would evaluate every single study that we run. Is this the best thing we need to do right now? Is this the best study I'm supposed to be running? So that's kind of what I think of. You may have heard of, like from the beginning of the replication crisis, one of the case studies of it was the BEMS extrasensory perception studies. So that was one of the things that failed to replicate early on. And there has been a lot of evaluation of these studies, right? There was a lot of criticism. There was criticism of the methods. There was criticism of lack of theory. There were papers written on how the study was not capable of testing the hypothesis that it was making, that people had precognition, that the study wasn't capable of testing that. So running, and there are so many different replications of BEM studies. To me, that's completely unethical. We know that that is not a good study. Why run it again and again and again and again? That is a waste of, human subject time. That is a waste of research resources. That is a waste of researcher time, basically, or the university's time that they're spending on research. We know that these studies don't show what they claim to show. It's just like we have invested so much in that piece smaller than 0.05 thing, that now we try to justify why that is wrong, pouring all the resources instead of using our reasoning and what we understand of research just to say that that's just a bad study. Let's not rerun this. And I do not think it's unscientific to be interested in the question of precognition. I think if someone really is interested in that, they should design a better study, not keep replicating BEM studies. That's ridiculous. Like, you're not going to show that that is a poor study and we should not believe in precognition based on the results of a replication. You should not believe that in the first place by reading the paper. So I think, I think the ethical aspect is extremely huge, and we should be vetting every single replication study, just we should be vetting every study.
Mhm. Yeah, Phil, you have your hand raised. Thank you.
Yeah, I think the ethics question is also, it's not very clear or easy to answer because it depends. Let me just give you an example again from my own experience. We don't want to use animals unnecessarily or human subjects unnecessarily. But what if use of animals or humans in a replication study is done in an experiment that the user knows is not going to replicate because the original paper was flawed and had questionable results in it, but it was published in a high-profile journal and received tons of media attention. Okay, when that happens, those studies tend to draw a lot of interest from the public, from companies, and from philanthropy. And when that happens, you start to see drugs or interventions start moving towards clinical trials and clinical trial design. But if the study's flawed and you are charged with replicating and you chose to study it because you know there's intrinsic defects in the experimental design or how it was done, and your goal is to prove that it's not correct, you might save hundreds of millions of dollars in future drug development. And that's exactly what happened with a couple of studies that we saw come through our replication committees. So it really depends again on how you think about it.
Yeah, thank you. That's a great example. And one thing, so I'm just going to we're running out of time and we have 10 minutes left. And I just want to get to some of the questions from the audience as well. So, I mean, I think that, Phil, that was a useful example of something we can do and the ways in which a replication study can be helpful. We've talked a lot about the ways, the sort of methods and tools that have been used as a community may not be the things that are going to resolve some of these concerns. Jan Weissenberger has asked something that we haven't discussed yet, and that is sort of the role of systemic reviews and meta-analyses in helping to address the lack of reproducibility in research. Do these methods help us? Do they also have pitfalls? What are your thoughts?
I mean, I can speak to, again, in my field, meta-analyses have actually been done on a number of studies around individual drugs that have been tested for a specific purpose in spinal cord injury. And what they have shown almost consistently is where the flaws in the studies exist. What are the outcome measures that are being used that are consistently low sensitivity and are overestimating the result or the effect size that is being described in the paper. So I think there's a lot of value in that. The reality is that most people in my field and likely in a lot of other areas of biomedicine aren't going to run meta-analyses. And you need people that's what they do. They're going to spend their time on it because you create enemies. You start running meta-analyses on your colleagues' papers and saying, your papers are crap. You're not going to be very popular, and your grants are not going to get funded. And that gets into a whole other area of why replication studies are hard to do, because people don't want to cooperate. But I do think, Jen, to answer your question directly, meta-analyses in particular can be very useful. And if there was a third-party independent source doing the meta-analyses in individual fields, it could provide some insight.
I think one thing I want to add to that, and I think Phillip really made a great point about potentially positive, informative uses of meta-analysis. If we use meta-analysis to only kind of come up with an average effect size estimate, that's a bad use, because then it's kind of a garbage in, garbage out. If you have poor studies that are big, that's going to overwhelm all the other evidence. But the right way to use meta-analysis is to really have this careful, critical view at the literature, find out the weaknesses of the studies, find out the, again, sensitivity analyses, to find, how sensitive the effects that we find are different aspects of study designs, that's extremely helpful. But yeah, I mean, sometimes they're used in the wrong way completely. So what you get is the summary of some very poor data.
Mhm. So we have, I think, time for one more question, and that's sort of one question we haven't focused so much on is this idea of who should fix the problem? Like, and so let's think about who is responsible, or, it doesn't need to be, one entity, but how should we think about the different roles of responsibility in addressing some of these concerns? So David Adams asked really early on about addressing problems within social psychology, right? So one question is, should each of the disciplines focus open inquiry, right? Be curious about the sort of methodological concerns and fix it independently? Should institutions, research institutions, have responsibilities? One thing that Elizabeth already brought up is sort of starting some of these repositories for journals are starting to engage in some practices that support reproducibility, right? So one question is, should journals be responsible? And then finally, should funding sources like NINDS, HHS, how should we think about the primary agents when it comes to some of these concerns that we brought up today?
I mean, I can answer. I'll try to be very brief. I think that each discipline is going to have to manage their own unique problems. Certainly there's going to be a lot of overlapping similarities across disciplines, but there are going to be some unique things that need to be managed. And I think I've spoken a lot about the things that we've done within my specific area of expertise, and there's been a ton of focus on these topics. So, given that, and the fact that we still have an inability to reproduce and replicate, it gets right back to the point that it's not really a crisis, it's part of science. And I think that I would actually spin this a little bit differently. And then, I would say to the NIH director, for example, who's propagating this chaos theory, is that maybe we should be talking more about a communication crisis, because scientists are really pretty good at policing now and looking at all these problems. But what we're not good at, and I would say this is probably true across most scientific disciplines, is communicating to the public, communicating how we do what we do, why we do what we do, and why things are the way they are. I mean, most people only see the end product. Berna showed a great slide with all the magnificent things that science has yielded over time, and those are all built on the shoulders of reproducible basic science, right? Those all led to those major discoveries. We don't talk about any of that. We just talk about the end game. And I think that most scientists just aren't comfortable, and they're not trained to communicate effectively with the public. And that's, to me, one of the areas where we could fix a lot of problems if we were forced into trying to explain what we do to the public.
I'd like to build on that a little also and I would go one step further and say not just communicating to the public, but internal communication within disciplines. I think we can all learn from each other in different ways that, different fields, there are different problems, there are overlapping problems, and there are analogous problems. And I think that we can learn from how each different disciplines address those challenges. And Phil, I particularly loved your suggestion that the incentive structures need shifting, and that's so much of the science is learning from our mistakes, learning from our failures. That's how we move forward. Oh, hey, this thing didn't work, but what if I tweak this, measurement here, I tweak this parameter there, a lot of how we come up to that final product isn't documented, or it's not clear. And I know many students in computer science are self-taught in some areas from just going in and reading through the documentation and looking at the commit history in GitHub, because you've got the whole version like, oh, hey, this parameter didn't work, so now I'm adjusting it this way because of whatever. And you can actually see the process. None of that makes it into the paper at the end. But when you can go back and actually look at the process and try to understand, well, why is this particular function written this way, as opposed to, you know, the equivalent, maybe why did we, like, why did you sever the spine or create the injury in that particular manner? Getting at understanding why these small decisions were made, because that impacts the outcome. And I think there's a lot to learn from what other people have tried. Otherwise, you know, we may be doing a lot more replication studies in science than we realize because we're trying things other people have tried that didn't work.
Thank you. And Berna, you could have sort of the last word related to this question.
Oh, okay. So I completely agree with the communication problem that both Phillip and Elizabeth have touched upon. Yeah, definitely we have an issue with science communication within and outside, like to different kinds of communities. I'm also going to say that with respect to where does the ethical responsibility fall, and there was something in the prepared questions that you sent that I personally will say that I'm completely against surveillance, like any kind of centralized surveillance mechanism in science. That's not the way to go. That's very authoritarian approach to science, and it's not productive. So yeah, I think the ethical responsibility should be shared. It's at the individual level, it's at the fields level, like every field needs to identify their problems, but as individuals also, we really need to take responsibility in how we, not only how we create research, but how we consume research. A lot of those that, a lot of the problems that we experience with the kinds of things that Phillip said, when something is published and it's completely garbage, but it turns into a huge thing because it's a high profile publication, now people follow that. I think it's each of our responsibility to not fall for that. Just because this was published in Nature, in Science, it's got to be true. So I'm going to base like my research on that, and I'm going to kind of riff off it. That's not how research should be done. I think we should be taking responsibility in how we read research to begin with. Like each of us should be better consumers of research. We need to understand uncertainty. We need to appreciate uncertainty in every study and stop taking like individual study results as facts that, you know, to the established facts. And that's going to fix a lot of problems, I think, if we change our attitude about individual studies and kind of look at research in a more programmatic, long-term manner. So.
Well, thank you, the three of you. I actually feel like really hopeful after this conversation. It felt like a lot of the sort of suggestions brought back agency and curiosity to the independent researchers. Like there's things we can do as scientists. There's also incentive structures and other things that need to change as well. But thanks so much for sharing your wisdom and being models of scientific communication to the public. I learned a lot, and we will, to the participants that are still there, join us in December for our final CARE panel for the semester on whether or not AI models can replace animal models when it comes to some research. So we're going to be talking about some similar themes. I hope you can join us then. All right, talk to you all soon.
Thank you. Thanks so much.
Thank you.